one thing we know. What's inside an atom? What's one thing inside an atom? The nucleus. There's a nucleus inside the atom. What are we going to find inside the nucleus? Something inside the nucleus. Protons. And what else? Neutrons. What else? So protons and neutrons are sometimes referred to as subatomic particles, but there's one more. What's the other one? Electrons. If something is neutral, what's going to be equal among those subatomic particles? Protons and neutrons. If I want to know what protons and electrons. Something is neutral, the number of protons is going to equal the number of electrons. If I want to know what element I have, what number is important?
The number of protons.
The number of protons. And just to make sure we really clarify something, we have been using back and forth the idea of proton number and atomic number. I'm going to attempt to stick mostly with proton number because that's the terminology you'll see in the Cambridge material when you take the test. Same thing with nucleon number and mass number. You're going to more often see the term nucleon number. They mean the same thing. In my test, I will probably give you both because I don't want you to get confused with my test on the two of them, but I also want you to be familiar with the terminology as we move towards Cambridge exams. So nucleon number tells us the number of what two subatomic particles? What do we add together to get the nucleon number?
The mass and
The protons and the neutrons. So those are some things that we know that we've led up to this point being able to see. We have been using an idea for a number of days now without really clearly defining how we got this idea. And this idea has to do with the mass of protons and neutrons and electrons. Now, one of the things that was important to be able to find the neutron was actually to be able to measure the mass of atoms, to measure the mass of a proton. And so when the masses of protons and neutrons and electrons are measured, it's determined that the mass of a proton is around 1.67 times 10 to the negative 27 kilograms. A neutron, 1.6749 times 10 to the negative 27 kilograms. And then the mass of electron, 0.00091 times 10 to the negative 27 kilograms. Are those big numbers, small numbers?
those are
Really small numbers.
Incredibly small numbers, right? And not necessarily the easiest to work with. And so in a couple minutes we'll see what it is that we already have been using and that scientists consistently use when they're working with protons, neutrons, electrons on a daily basis. What do you notice, any similarities that you notice here? If you were to compare anything, what would you compare?
what they connect it with.
The negative 27. And by having them all set in scientific notation to the same power of 10, it makes it very easy for us to compare other things about them. What else might you compare? What else would you notice that is similar? Miranda, anything else that you know is similar? Okay, by 10. And so I think you guys have worked a little bit with scientific notation with Mr. Brandon. It's an incredibly useful thing in math, right? And we'll run into it some here. In addition to the fact that they're all set by 10, multiplied by 10 to the negative 27, they're all reported in kilograms. Is there anything else that would be similar here? CJ, what do you think? Any masses that are similar here? Maybe not identical. The proton and the neutron. They're not identical, but they are very close. And when we're talking about such incredibly small masses, we really are saying that these two would be very, very close. But if I was to compare the mass of an electron with either of these two masses, what would I have to say about the electron? Denise, what do you notice about the electron? Here we have the proton is 1.67, the neutron 1.67. But look at here at the electron. It's a smaller number. It is a lot smaller. So one of the things that we know is that when we look at the mass of an atom, if we're looking at a helium atom, we look at the mass of the whole atom. Most of what the mass is based on the proton and the neutron. And the electron is almost insignificant how much it adds to it. That's going to be important in what we see about how we use these. The other thing, I'll get this up where you can look back to it, but I'm not expecting you to memorize those masses, okay? There's the other ones that we use, I expect you to memorize, and so hopefully you can handle memorizing the other ones. We'll see if you can when we get there, okay? Charges. We've also worked with charges, but we've just been saying things like, what do we usually say the charge of a proton is? Positive, and the charge of an electron, negative. But just like masses, the charge of the proton and the electron, and even the charge of the neutron can be measured. What is the charge of the neutron when it's measured? 0. And the C stands for coulomb, and coulomb is a unit of energy. So the neutron has a charge of 0. It's actually part of why it was really hard to discover, because it's hard to discover things that we can't see that don't have a charge. But what else could we say here if we were to compare the proton and the electron? Martine, tell us something about the proton and the electron, about their charge.
Neutron.
Yeah, so we have a charge here. What's the charge? Just the first two numbers. 1.6, and we say times 10 to the 19, right? How about the electron?
Negative 1.
Okay, what could you say about the two of those? They're almost the same, and there's only one thing different. Brandon, what's the one thing that's different between the charge?
One's positive, one's negative.
One's positive and one's negative. And we've been using that, right? We've been using that for quite a few days. So instead of using those values, instead of expecting you to memorize, or any students really at a high school chemistry level to memorize things like the 1.6 and the 0.00091 and all of that, we use something that's called relative charges. And I do expect you to memorize these. You think you can handle it?
Yeah.
You can't handle it, Martine? I bet you can. Relative charges, relative mass and relative charge. What is the relative mass of the proton?
1
Positive.
versus
Karen,
1.
would you get the line? Would you mind giving that one? So, the proton, the relative mass is 1. What's the relative charge? Positive 1. If I was looking, what this means is that when I'm looking at a particular atom, and I say, well, that atom has 1 proton and 1 neutron and 1 electron, what would I say the mass of that atom was? It has 1 proton, 1 neutron, and 1 electron. What's the mass of that atom? Let's set 1, right? Here. What we did yesterday was we even looked at this. So if I have something like, let's even go back to helium. And we have a helium atom that has 2 protons, 2 neutrons, and 2 electrons. If I want to know the mass of that, how much mass are these 2 protons contributing? Just the protons? Each proton has a mass of 1, and I have 2 protons, so what are they adding to the mass? 2. So if I was to say the mass, the neutrons, what are they adding to the mass? I have 2 neutrons, each one has a mass of 1. 1, 2, right? 2 protons. So we have 2 protons with a mass of 1, right? 2 neutrons also with a mass of 1. So we add 2 more to this mass. We didn't really talk about units.